Alright, so let's first recall that r xy is equal to the sum of xi yi minus n x bar y bar over the square root of the sum of xi squared minus n x bar squared times the square root of sum of yi squared minus 1 n y bar squared. This is the sample correlation coefficient. Okay, so we're going to talk about properties of this thing. Okay, so first thing is that if you look at a unit, the numerator has unit is the unit of x times the unit of y. In the denominator, the first term is the unit of x, the second term is unit of y. Basically, they all cancel each other, so r does not have a unit. Hence, that's why the name coefficient comes from, because it doesn't have a unit. Okay. And the second one is that r is always between 1 and -1. So in the extreme cases, if r equal to 1, this means xi and yi can be perfectly fit onto a line, straight line with positive slope. So for example, we have seen the previous video, the 1, 1, 2, 2, 3, 3, 4, 4, 5, 5 fit perfectly onto the line. Y equal to x, which has positive slope. Therefore, the correlation is equal to 100%, which is 1. And the other extreme case is if r is -1, then xi, yi can be perfectly fit onto a straight line with negative slope. So for example, we also saw this in the previous video, the 1, 5, 2, 4, 3, 3, 4, 2, and 5, 1 example. These 5 points fit perfectly onto the line y equals to 5 minus x, which has negative slope. Therefore, the correlation is -1. If r equal to 0, then we say xi and yi are uncorrelated. So if you plot them on the plane, you will be scattered around and no trend or pattern. Alright, so these are some properties. There's more properties. Let me shift it down a little bit. So if you calculate a sample correlation between x and y, it's gotta be the same as the sample correlation between y and x. So it doesn't really matter which variable you put first. The result is gonna be the same. And the sample correlation coefficient doesn't change if you add x and y each by a constant. That means this is invariant under shifting, or what's called a translation. So if you add all the xi's by the same number and add all yi's by the same number, the sample correlation does not change. And same thing when you scale it. So if you scale all the xi's by a scalar alpha and scale all the yi's by the scalar beta, the sample correlation does not change if alpha and beta are positive. So that means r is invariant under positive, important scaling. So you might ask, what happens if alpha and beta are negative? Then if alpha is less than 0, then the relation between alpha x and y is going to be the negative of the relation between x and y. So if alpha is negative, then it flips the sign of the sample correlation coefficient. Okay, so because of this property, realize when you calculate real-world problems, for example, if you want to calculate a correlation between height in meters and weight in kilograms, this is going to be the same as the correlation between height in feet and weight in pounds. Because to convert height from meters to feet, you multiply by a constant positive number. To convert weight in kilograms into weight in pounds, you also multiply by a positive number. So the correlation coefficient is going to be the same. Same thing if you want to calculate, let's say, spring temperature in Celsius versus fall temperature in Celsius. This is going to be the same as the correlation between spring temperature in Fahrenheit versus the fall temperature in Fahrenheit. Because when you convert between Celsius and Fahrenheit, all you do is you multiply by a positive constant and you add or subtract another constant. So our value does not change. So this is saying that when calculating R, the choices of units don't really matter. You can choose feet, you can choose meters, you can choose centimeters, you can choose inches. The correlation coefficient is going to stay the same. All right, one last note. This is a big bullet point. You have definitely heard this before. So correlation is not the same as causation. So the most common example is that if you study children and xi be the feet size of the children and yi be the vocabulary amount, basically the amount of vocabulary this child knows, then if you actually calculate the correlation coefficient, you realize that x and y are positively correlated. But this doesn't mean that larger feet implies that this child knows more vocabulary. And the reality is there's a third factor, which is older in age. So this is the third factor, which causes both of them. Like if a child is older, then this child likely has larger feet. If this child is older, then this child likely knows more vocabularies. So the third factor causes larger feet and more vocabularies. So that's why these two are correlated. But that doesn't mean a child having larger feet implies that this child knows more vocabularies. All right.